Gyroids. They are one of the most complex and beautiful forms in mathematics, but creating them in Grasshopper often involves confusing plugins or complex equations. What if you could build this entire parametric structure step by step without any of that? In this video, I'm going to show you exactly how to do it. By the end, you will have a powerful, flexible script that you can morph onto any surface you can imagine. First, we'll set up a few simple inputs. We need a number slider to control the overall size of a single gyroid unit. Think of it as the dimension of a cube. Next, another number slider to control the smoothness of the final gyroid mesh, which will be an integer from 1 to 8. The other inputs x, y, and z count will be used later on to create arrays from our finished module. Now to create a single gyroid, we start with a cube. Let's use a center box. Now the x, y, and z dimension of the center box will come from the single gyroid size. Now remember, since these values represent the half of each side of a cube, we divide this number by 2. With our cube in place, we will deconstruct it using deconstruct brep. From the 6 faces, we only need 3 specific ones that will form 1/8 of our final gyroid. We'll use list item and extract indices 2, 3, and 4. Set this to multiline data and connect it to the indices. Now for the intricate part. From these 3 faces, we need to isolate the edges in a very specific sequential order. To get this, let's deconstruct the brep. Identify the edges as per the current order. We use curve middle. Use point list with a size of 10. So the order in which we need to extract these edges are 2, 1 from the first face, 1, 2 in the second face, and 0, 1 in the third face. Use partition list to structure these indices in a correct order. Two indices per face, and then use list item again to extract naked edges from these surfaces. We would need the interior edges as well, so use the same indices with cull index to get the remaining edges. Next, we'll create gyroid signature curve, which would move something like this. We do this by moving the midpoint of each of the naked edges using vectors. Extract the middle points. For vectors, the pattern is a positive move in X, Y, and Z, followed by a same pattern but in negative, which is X, Y, and Z. For the factor, we go back and use the same value over here, which is half of the edge of the cube. So these are three vectors in the positive direction. Merge it together. Then the same pattern in the negative direction. Merge these. Remember to partition this list to structure them correctly. And once we have the vectors, use the move command to move the middle points. After moving the midpoints, we'll use NURBS curve to create the curved edges. To create the curved edges, we require the start and end point of these edges. Use the endpoints of this input and merge the start, midpoint, and end. Before we start merging them, it's advised to graft these. So we get 3 points per branch. Now connect this to the vertices and we get the curved edges. We need to merge these curved edges with the respective interior edges, which were over here. And for a successful merge, need to ensure that both data structure are aligned. So shift path over here, and notice how this is orange. That's because the degree is set to 3. Set this to 2 and this should be fine. Now use the merge component. Bring in the culled index. Join these. Simplify the input of culled index. And simplify the input over here. And we get 4 edges per branch, which can be joined. Now the reason to join them is because we want to convert this into a surface. And to convert this into a surface, we use edge surface component. This requires 4 curves in a correct order. So by joining them and subsequently exploding them, we get the curves in a ordered structure. Use list item and connect each index with each of the inputs, and we get 4 surfaces. These surfaces form the building blocks of our gyroid. Now we have our base surfaces, but they are rigid. To get that beautiful organic gyroid shape, we need to relax it into a minimal surface. For that, we will use Kangaroo. First, we need to convert the surface into a mesh. To get a clean result, I'll use isotrim and divide domain square. Now the U and V count would determine the smoothness of the surface. Connect this over here, connect this over here, and by default this is set to 10 and 10. So here we bring the value set at the start. Connect this to the U and V count. Now, a key point to remember over here is that the number of divisions over here would determine the smoothness of this surfaces, but increase this number to more than 8 or even something like 6 or 7 would dramatically increase the number of faces, which would then make the entire geometry lag when you're doing array operations or surface morph operations in towards the end of the script. So it's advised to keep this number to 4 or 5, but depending on smoothness you can increase this as well. So if I increase this value to a 5 or a 6, you see that the number of subdivisions increase, but it will also slow down the script later on. So I'm going to set this to 4. Take the surface. Now once I have these surfaces, we need to convert this into a mesh. For that, I use simple mesh, and now I have 16 faces. Flatten these, get 28 faces. Now couple of things to join them into a mesh is to unify mesh normals. I use this component followed by mesh join, followed by mesh weld vertices. And you should receive a mesh like this. With this mesh, we are now going to apply Kangaroo goals to relax this into a smooth mesh. As you can see, this is still a very stiff mesh. So for Kangaroo, we bring in the zombie solver. For goals, we use 3 goals. First one being show. Second one is edge length. And the third one is anchor. For anchor, we need to extract the naked vertices. So we use the naked vertices component, which is part of Kangaroo. Connect the naked points. Set the target value to something really high. Set the strength value to something really high, which is already 10,000, so that's fine. For the length factor, we send this to 0.2 and connect the mesh. And connect the mesh over here. Merge these goals. Set the maximum iteration to 500. The reason I set this to 500 is to ensure that if I make any changes to the smoothness or the size, this can compute fast and it does not take time, because by default this is set to 50,000. That will take a lot of time to compute. So I set this to 500. And the output is a set of mesh, lines and some nulls. And we need to extract the mesh, which is the first item. Hide everything. And the mesh is a smooth mesh that we expect from our gyroid. If any of these Kangaroo goals are new to you, I've created separate videos explaining them in detail. I'll link those in the description below so you can check them out. Now the mesh that we receive over here, which is relaxed by Kangaroo, can sometimes deviate slightly from our original anchor points. Here's the original mesh. Here's the new mesh. And if we zoom in, you'll notice the slight deviation. This can cause small gaps when we assemble the final gyroid, which is essentially the repetition of this form in multiple arrays. To fix this, we deconstruct the mesh. We identify the vertices which form the naked vertices, and that's already available to us over here. So we simply use replace items, wherein we take these vertices as a list. We want to replace it by the actual original vertices of the original mesh, which is over here. Remember, we are only replacing the naked vertices and not the internal vertices. For the indices, we already have, so the index goes and gets connected to indices, and the points gets connected over here. And then we take these vertices, these revised list of vertices, and we use construct mesh with the new set of vertices and the faces information coming from deconstruct mesh. And as a final check, zoom, just checking this again. We replace 37 items. Here's a list of vertices, list of indices. Okay, so the mistake I made over here is to connect the list of naked indices over here and the naked points to the items. And now we see that the points of the naked vertices perfectly align with the original mesh. This guarantees a perfect seamless result when we mirror and array this single 1/8 portion of the gyroid. With a relaxed 1/8 unit complete, the next step is to mirror it to create full gyroid. We'll use a 2x2x2 box array to create 8 copies of this piece of mesh. Now here's the mesh, but to create a 2 by 2 by 2 copy, we need to give it the size, the cell size, which can be extracted using bounding box. So that's the 2 by 2 by 2 array. Now within these, we need to flip some of these to ensure we get a complete gyroid. And to flip these, we would need the center point for each of these individual gyroids. So at this point, let me extract the centroid and merge this and the centroid together. I flatten this and we get 8 set of meshes and 8 set of center points. Now I explode this tree to get the mesh separate from the points. Now we need to flip or mirror some of these pieces to get them aligned perfectly. Through testing, I found that we only need to mirror 6 out of the 8 pieces, leaving the first and the last as they are. We'll construct a series of XY, YZ, and XZ planes for each set of mesh to be flipped. Through testing, I know that I need to merge these and then merge these again in a reverse order. So I connect this and I reverse the list, creating plane origin. So that's the origin and that's the base plane. And before I do this, like I mentioned, we only need to operate on 6 of these 8 meshes. So I can use list item and remove index 0 and -1 because first and last need not be touched. So here are the 6 center points, and to get the 6 meshes corresponding to these 6 center points are over here. Now I use the mirror component and flip these. If I hide everything else, you can see it's starting to form the gyroid shape. I'll also connect the missing 2 pieces which we extracted earlier using merge. These are points, so I need to extract the mesh. Yeah. And let me just use a mesh component to visualize these. There you have it. your individual gyroid. These are 8 separate meshes which needs to be joined together. So we can flatten this, use mesh join, unify normals, and weld vertices. And what we get as a result is the single gyroid unit. Once you have the single gyroid, you can take it and create a box array. Using the geometry bounding box to get the cell size and the X, Y, and Z count coming from the count sliders set up right at the beginning of the script. And once this is set up, you may create an array, a box array of the gyroid form. You can change the size of a single gyroid. You can also control the smoothness of the gyroid. For more creative applications, you can choose 2 or more custom surfaces or create a custom surface like this, which represents a shoe sole. Create your own set of twisted boxes, which would appear something like this. Use the box morph component to take the single gyroid, which is over here, and morph it onto the twisted boxes. The resulting mesh can be joined, welded, and given a thickness that would make it ideal for 3D printing. And the final output would look something like this: a gyroid morphed into any shape with a certain thickness as per the 3D print requirement. As you can see, the entire script is highly flexible. You can control the size of a single gyroid. You can control the smoothness of a single gyroid, increase or decrease it. You can also increase the number of repetitions in X, Y, and Z direction. So it's highly scalable. This entire step-by-step tutorial is available on YouTube for everyone. But if you want to access my final organized Grasshopper file, it's available to download on my Patreon channel. When you join the All Access tier on my Patreon, you get instant access to this file and my entire back catalog of projects. It's the best way to support the channel and get a valuable professional toolkit at the same time. Thank you so much for watching. I hope you learned a valuable new technique today. If you did, a like and a subscription would be amazing, as it truly helps the channel grow. I'm always creating new projects and I can't wait to see you in the next one.